This is a walkthrough of the solutions for the COS217 midterm from spring 2020, problem 1. In the first part of this problem, the students were asked to determine what decimal integer was printed by each of 5 printf calls. In the first item, we have 3 separate addends, so we'll take them one at a time. OX21, OX indicates that it's a hexadecimal literal, so that means that we have 2 times 16 plus 1 is 33. 7 is just 7, and 0217, the 0 indicates that it is an octal literal, so we have 2 times 8 squared plus 1 times 8 plus 7. So that's 2 times 64 is 128. 8 and 7. When we add this together, we get 183. In the second item, we have a bitwise knot, aka the ones complement, of the unary negation of 1. So let's start out by figuring out what is the bit pattern for the unary negation of 1. In order to do that, we need to figure out what is the bit string for 1 itself. These are integers. On our machine, ints are 4 bytes, so that's 32 bits. 1 is going to be 31 bits of 0 and then a 1. To get the unary negation, that is to do -1, we have to take the 2's complement. 2's complement, we're going to flip all the bits and add 1, so that would be all 1's and a 0 plus 1, which is all 1's. So -1 is all 1's. Now we have to take the bitwise knot of that flips all the bits. That yields a bit string of 32 zeros, which is just 0. In the third item, we switch the order, the unary negation of the bitwise knot of 1. 1 is still 31 zeros and a 1. We flip all the bits, and we get 31 ones and a 0. We now need to take the negative of this. How do we take the negative of it? Again, we're going to do the 2's complement algorithm. And so when we do 2's complement, we flip all the bits and add 1. That's a whole bunch of zeros, 30 of them in fact, 1 0. And that is 2. In the fourth item, it starts off with a trick. Because we've been doing bitwise operations, and there's another in this one, you see that less than sign and really want to think that it's less than, which would be left shift. But there's only one of them, and so this is asking to start off going inside to out. 255 is less than 8. That's false, which we interpret as 0. And then when we do 0 as an integer in bits, that's 32 zeros. We take the bitwise knot of that, so we have 32 zeros, knotted becomes 32 ones. And as we just saw above, that's going to be -1. Finally, in the last item, we have 2 XOR 2. Recall that XOR means that it will be true, or 1, only if the two bits that are being XORed differ. So let's start out by figuring out what 2 is. 2 is 30 zeros and then 1 0. Negative 2 we can find by taking the 2's complement. That's flip all the bits to the left of the rightmost one, or flip all the bits and add 1. So if that was 2, negative 2 is going to be all 1s, 1 0. Now we XOR them. When we XOR, 0 XOR 1 becomes 1. They're different. And that follows all the way down until the last 2 bits, in which the last 2 bits are the same. So we have all 1s and then 0 0. This is the result, but now we have to get it back into decimal. We see that the leftmost bit is a 1, so that means it's a negative number. Let's put that there before we forget. And now we do the 2's complement algorithm yet one more time in order to determine what the magnitude is, what the positive number is that is the negative here. So we flip all the bits to the left of the rightmost one, or flip all the bits and add 1, and that gets us this bit string, 29 zeros, 1 0 0, ones, 2s, and 4s, so that's negative 4. In the second piece of this first problem, we're asked to fill in the table, giving a type and a value for each literal that has something to do with the digit 0 or the value 0. For the values, we're asked to just write 0, small, or big. So let's start out with the literal 0. It is an int, because we know that it would have a U or an L after it if it were unsigned or long, respectively. Without that, a numeric literal is just an int. If it doesn't have a decimal point or a E somewhere in there, it has neither, so it's an int. Its value is, in fact, just 0. It is 4 bytes, that is 32 bits of zeros. The next two have these single quotes. We identify these as char literals, so let's write that. Now we have to consider their values. The second one of these char literals is \0. We think of this as the null byte. What that means is it has 8 bits of zeros. If that's the case, that means that its value is in fact 0. For the char literal that has the 0 there, we know it's not 0. Instead, we have to remember that chars are really just very short ints. They're 1 byte ints. And char literals are translated to int using the ASCII table. So the char 0 is ASCII 48. You didn't actually have to know that. You just had to know that ASCII values are from 0 to 127, all of which would fall under small, except for that null byte that we already addressed. So it is small. We can fill in and actually follow the problem's instructions and write 0 instead of 0. Either would have been accepted. For the fourth item in the table, the string constant 0. The string literal 0 is a string, but what we know about that in terms of a type in C is this is a char star. String literals are implicit pointers that point into the RO data section where the characters for the string reside. That means the value of this implicit pointer is that address in RO data. The address in our data is certainly at least 128. In fact, it will be much bigger, and thus we can write big. Finally, null. Null we think of in this class as the pointer that points at nothing or to nowhere. Because of this, we assign it a void star type. However, in the C standard, it is in fact an int literal that just must be guaranteed to be castable to void star. So int is perhaps the better answer, but in the context of 217, void star was the expected answer. Both were accepted. And its value is 0. In part C of problem 1, we're asked to consider symbolic constants defined by an enum type. In the main program, we're just printing out the 5 values that are defined in this enum. And so when we start, we can say some of them are explicitly defined, others are just implicitly defined. They are not given a value explicitly. We have learned that for enums that are not explicitly given a value, they begin at 0 and count upwards. So in is 0, the is 1, service has a value given in the enum, so it keeps it. Same with of. And humanity is another one that doesn't have an explicit value given, but it follows the same rules as the other ones that we've seen without an explicit value, in that it just follows one after the previous enum member. So in this case, 1897. The final part of problem 1 asks us to consider a program with a switch statement. A switch statement is a conditional. If there were breaks in every case, it would look exactly like an if-else, 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 if-else clause that strung out with a chain. But in this case, we don't have a break in every statement, so in every case, so we have to do a little bit of tracing. So, looking at A, if that's the input, then on line 5, we're going to switch on A. We end up in the case on line 6 here, where we will print out do, and then we see a break. Break takes us out of the switch, we print out our new line, and we return 0. For case B, which we will get from switching on the input B, case B, we will print out ray. But now there's no break, so we will fall through. We fall through to the default, which is a little bit unusual. Usually the default comes last. But in terms of fall through, either falling into it or falling out of it, default follows the same rules as every other case. So we fall into it, we print me. There is no break, so we fall through again into case C, where we print fa. Now there is a break, so we break out of the switch and we print our new line and we return. For C, we go into that C case, we print fa, break, the new line, and return. For D, we enter into our D case, we print so. Now there is no break, so we would fall through. However, there are no cases left, so falling through still exits the switch statement. We print our new line and we return. Finally, in the case of E, this doesn't match any of our explicit cases, A, B, C, or D, so that is where our default gets triggered. So we will start in me, The default doesn't have a break, so it falls through to fa, which breaks and prints the new line and returns.